To start. Um, Ketevi, you ready?
Yes, I am.
Okay. So today we're very happy to have Ketevi here, and he's an experimentalist in the Atlas for the Atlas group at the Large Hadron Collider. Ketevi was born in Gabon in Central Africa, and then he moved to Togo, where he stayed through college. From there, he went to the US and he earned a PhD in nuclear physics from UVA. And after UVA, he did postdoctoral stints at Jefferson Lab, Hampton University, and CERN. And in 2001, he had joined the Brookhaven National Laboratory. Now, it's this postdoctoral stint at Jefferson Lab where I met Ketevi. And it's just interesting. One of our previous speakers, Ketevi, was Keith Baker. It
Okay.
seems like all of, well, certainly, maybe I should just speak for maybe minority African Americans, that somehow we always tend to come from certain points, certain programs,
That's
especially in
right.
quantum physics.
Yeah.
So Ketevi in Atlas, his career skyrocketed and became a bit of a celebrity, especially from my perspective. I was just telling Ketevi how I remember him holding court at CERN every time I would visit. In particular, from 2008 to 2010, he was the convener of the Atlas Working Group. He's also been the coordinator for Atlas on minimal bias interactions, and also the coordinator for mini Atlas physics analysis tool. So since 2001, he's been focusing on the Higgs boson and exotic physics associated with the Higgs boson and other exotic physics at the LHC. In addition to all of this, he is the main organizer for the African School of Fundamental Physics and Applications, and I hope that he will give us a little bit more about that later on today. And also, Ketevi, I'm waiting for my invitation to come.
Yeah, definitely. Yes. Yes.
And of course, last year he was elected to the African Academies of Sciences. So for this particular colloquium, if you can raise your hands, if you have a question or go into the chat, I'll recognize you and your microphone will be unmuted so that you can give your question. So Ketevi, of course, is going to tell us about searches for dark sectors, states, and exotic Higgs boson decays at the LHC. So let's welcome Ketevi.
All right. Devin, thank you very much for the invitation. It's my pleasure to be with you today. Devin had invited me before. I was expecting to come there in person, and I hope that the future will allow us for us to meet. In the meantime, I have a pleasure to give you my perspective of what I do as research in physics, which has focused on search for dark sector state in the decay of the Higgs bosons. I will try to clarify what we mean by dark in the subsequent slides. So what I will do is that I will review the discovery channel of the Higgs boson and also some of the property measurements. Then I will make the case for extension of what we call a standard model into what I mean by dark sector state. And then I will discuss a few selected searches of this exotic dark sector state. So we know that our universe is really large. It started almost 14 billion years ago. Physicists claim that there was a bang, which we call now the Big Bang theory, and we've been struggling to understand what the universe is made of. We want to understand what happened at the beginning during the Big Bang. And another big question is, what will happen in the future? What's the fate of the universe? Yeah. So those are really huge questions, and they invite physics to try to bring some answer. answers. They invite philosophy to, think about some answers, and they also invite religion to also bring answers. And that just tells you how complex the whole situation is, and we really cannot understand it all. And so on the scale of size, you see, for example, at the beginning, what happened at the Big Bang, and then, all of these things are in centimeters. And then when we believe protons and atoms were formed eventually, we human beings appeared, and we know that, we also are made of matter, which when you scrutinize it, we understand that matter has molecules which have atoms, and atoms have a very centered nucleus with an electron cloud around it. And if you inspect the nucleus further, then you see that it has protons and neutrons. And today we understand that even protons and neutrons are not fundamentals. They have even more fundamental objects or particles bound inside them that we call the quarks. Now, what is beyond that, we don't know. But we can point to the sky, and we see large galaxies through our telescopes. We can see stars. For our naked eyes, see other planets and so forth. And then when we want to understand better, we have designed what we call accelerators to really scrutinize some of these things in detail. So these accelerators are helping us to understand the microscopic aspects of matter and force interactions. And so now we have been successful at connecting the study of the minute elements of matter, which we cannot see or cannot study with our naked eye, with the study of very, very large scale structures, which some of which we can see with our eyes, others we can't because they are too far away, but they are very big. And we're trying to connect our understanding on that large scale. And it is daunting, and it is really huge. If you think of it in terms of when things happen along this big cosmic scale, then from the Big Bang, around 1 picoseconds later, maybe matter start appearing, maybe we don't know. And then a bit later, we have the formation of protons and neutrons, and then formation of nuclei, eventually formation of atoms. And somewhere along the way, there must have appeared something that we call dark matter. So that's, physicists, anytime they don't understand anything, they put dark attached to it. That's basically, and we try to scrutinize what that is. Now, matter is certainly what we know. We are everything that we see, and, it's made of what we ordinarily call matter. And those things are bound together, or there are forces interacting between various forms of matter. So eventually, people started discovering other particles. They knew about the protons, they knew about the neutron, then they knew about the atom, they knew about molecule. And then, but people started noticing that there was a shower of particles coming from the outer atmosphere, and we are bombarded by these particles all the time. And they want to understand what's the nature of these particles. And there are simple devices that you can do. You can have, cloud chamber can tell you a little bit about particle tracks. And using Maxwell's equation and Lorentz force, you can roughly understand that there are various types of these particles. But then people want to study them better because when they are coming from the upper atmosphere, they come in different directions. They have different masses, they have different energies, and they have different rates. So to control their understanding, then we start building accelerators to really study them, very well. So then out of that study, we eventually come to start structuring our understanding of matter. That we know that there are various components, particles that form what we know today as the standard model, which describe, matter as we know it. And, so we have matter particles. These are the quarks, and there are 6 of them. They have been given some strange names, up, down, charm, strange, top, and bottom. But just think of them as different flavors of the same thing. Yeah, so you may think of them like, yourself, your brother, your sister, and so forth, but you are all related genetically, and you are essentially the same people, but you have, some different properties. That's basically the idea. And then all of these things have some interactions which are dictated or are driven by forces that we know in the universe. We all understand gravity. It describes things falling to the ground. It describes the rotation of a planet. The Earth going around our sun, for example, is driven by the same force. And we know about electromagnetism. We've learned about Maxwell's equation. People understood electricity and magnetism, and Maxwell demonstrated that these are just manifestation of the same force called electromagnetism. And Maxwell was at the University of King's College London. I borrowed this slide from Professor John Ellis, who is currently at King's College London. So then we can see that these fundamental particles form the cosmic DNA if you merge them with the fundamental forces. From here, you can build any structure of matter that we see. The detail may be very difficult to build, to understand, and it requires biology to give us some answers. It requires atomic physics to give us some answers. It requires material physics to fill in the gap. So this is by no means simple to understand, but the statement is that on the fundamental level, this is all you have. And then they interact and rearrange themselves in some complicated ways that require all the branches of physics to, flesh everything out and increase our understanding. But the basis is just what you have here for ordinary matter. But then the question is, what exactly is matter? We know these things, these particles exist. What exactly is matter? And that question seemed to have been forgotten by some of the giants in our fields. Yeah, when Newton was studying force and all of those Newton's laws, like gravity and so forth, we were taught earlier on that the weight of something is proportional to its mass. Yeah, and we know that force, is also proportional to mass. There is an acceleration and so forth. So the concept of mass is there, but nobody explained to us what exactly mass is. Einstein then came along later on and says that energy is proportional to mass, E equal to mc squared. That m is mass. But what exactly is mass? Yeah, we know energy is proportional to weight is proportional to it, but what exactly is mass? So then there was this gentleman, Peter Higgs, and he says, yeah, well, now I can explain to you what mass is. And he came up with the idea of the Higgs boson to explain where mass comes from for fundamental particles. By the way, Peter Higgs also is from King College London. So this is to show how many of these fundamental ideas have come out of those places. Now, so the Higgs boson was proposed to explain how mass arises for fundamental particles. And we understand that without the Higgs bosons, there will not be atoms, because electrons will escape at the speed of light. If they don't have mass, there will not be heavy nucleus. If the electrons have already escaped, there will not be the weak, what we call the weak interaction, which I didn't fully explain, but it's one of the forces that we have in nature, is responsible for radioactivity. The forces that drive radioactivity is what we call weak interaction. It will not be so weak. Life will be impossible because everything will just be radioactive, will just decay, and there is no mass. So you can see that this Higgs boson is really a serious concept. It's really a big deal. It's central to our whole existence. And you can think of it this way. Now, you know, I told you this collection of elementary particles, they all seem to have different masses. Another word, you know, they weigh differently, and we don't understand why. But here's how we can conceptualize it. If you take, you know, somebody on a ski, you know, and you have like those winter Olympics, you see those people on ski, they are whizzing, you know, going fast, and you're like, wow, this is really, you know, impressive. You know, so you can imagine that particle, I mean, that person who is just like moving fast on the snow, and, you know, with a ski, is like a photons, a particle without mass. You know, the snow is not preventing this person to go faster. I mean, in some ways, they are even, you know, using that to move faster. Then you have somebody with snowshoes and walking down the snow, but the person is sinking in, you know, and you can imagine that. You know, they're probably comfortable and so forth, enjoying it, but they are not going as fast as somebody on the ski. You can say that that person with snowshoes and who is somewhat sinking and going slowly has a heavier mass than the person with the ski. So the electron, for example, could be the person with the snowshoes. Then you have, you know, another person who, you know, a hiker and doesn't have proper shoes and is struggling to walk through the snow. That will be a particle with a large mass, and that particle, because the mass is larger, is interacting more of the snow with the snow, is dragged down by the snow, and therefore its mass is much bigger. So you can imagine the Higgs boson as, you know, the collection of these snowflake or these snow fields, and all of these particles, the skier and the person with the snowshoes and the hiker, are the different particles, and their masses is the, you know, arise through the interaction with the snow. Yeah, some have no mass at all, like the photon, the particle of light. Some have little masses, like the electron, and some have much larger masses, like the top quark. So that is more or less how to explain it. So this was all, you know, theory for a long time, and then, you know, the Higgs boson was searched for many, you know, in many experiments, and eventually people constructed the Large Hadron Collider at the boundary of Switzerland and France. What you see over here is the Lake Geneva. It's a very nice place, and you should go there when travel has resumed. And yes, the accelerator itself, it has 4 major experiments on the ring. It's a 27-kilometer ring, and all of the experiments, or these, you know, these experiments are underground. So you see that this ring here is going. Sometimes it goes under some villages, yeah, because these areas are somewhat populated. Okay, on the left over here you have the Jura Mountain. So there are 4 major experiments. There is the ALICE experiments. The objective of these experiments is to study that primordial cosmic DNA within the few picoseconds, and when you have, you know, a soup of particles, they have not, you know, condensed and grouped themselves into atom yet, and it's just, you know, some big plasma. They are studying that sort of thing. So they go back in their studies, you know, the things back in time at the beginning of soon after the Big Bang. Then we have the ATLAS experiment. So that's where I am involved. And also the CMS experiment. They are more like general purpose. They are looking for the Higgs boson. They are looking for new physics, things that we haven't thought of. They are designed to search for those things. Then there's the LHCb. You know, so the problem here is that we understand generally that we are living in a world of matter. They are there, electron is a matter particle. But we have also discovered that there are antimatter particles. For example, the electron has its anti-electrons that we call the positrons. They have all the same property except that the charge is flipped. People discovered that. It was first predicted by a theoretical physicist called Paul Dirac. Nobody was expecting it. And then it was discovered that there are antiprotons, antineutrons, anti-electrons. All the particles have their antis. Yeah? So that means, so all of those antiparticles, they form the antimatter. But the problem is, why do we see more matter in the universe today than antimatter? Because we understand that if you take matter and antimatter, you put them together, they will basically just annihilate. They will destroy each other and just give back energy into the universe, basically photons. So if they were created equal, our world would not exist. But we have no reason to believe that they were not created equal during when the Big Bang started. So something must have happened for our universe to be completely matter dominated. Maybe somewhere beyond, somewhere over there, there may be another universe that is antimatter dominated. We just don't know. So matter, antimatter, asymmetry, the fact that they are not equal when we look for it, is a big problem also in particle physics. We want to understand. Maybe that will also explain to us how our universe evolved. And this LHCb experiment has the task to try to understand that question. So if you go to Geneva, you go to CERN, the Lake Geneva is basically on the other side, coming out of the projection here. Those mountains in the distance there is the Jura Mountains. That's where the Jurassic Park come from, where they discover all of those things. It's related to the Jura Mountain. The Atlas experience here is underground. This is ground level there, and it's 100 meters underground. And here's the tunnel where, the tube where the protons, and they come through and they collide at the center over there. And out of that collision, there's a lot of energy that is released. Many things are happening, and then we search for new particles. Now, one of the reasons why it was embedded underground is to make sure that all of the radioactivity that come out of there, they don't come to the surface and bother people, because like I said before, the entire accelerator this 27 kilometers is going sometimes under villages. So this will be the ring of the accelerator. If you extend it, it will become that circular ring of 27 kilometers. So if you look at the Atlas experiment itself, this is huge. When you go to CERN, there's one building that we call Building 41. It's a 5-story building. If you take this Atlas detector and you just put it beside that building, you see that they are really of the same size. So imagine this detector, its radius, basically its diameter, is equivalent to the size of or the height of the 5-story building. And then its length is about 44 meters. So this is huge, and it weighs, 7,000 tons. So this is not just one tiny detector that you are going to put in your lab or under some basement room in the physics department. And it's also not a detector that a few people can build. This thing has been worked on by over 3,000 physicists and engineers, and look at how much it costs, almost $500 million Swiss francs. Swiss francs is roughly about, 1 Swiss franc is roughly about $1. And it has many, many different components, each of which are detectors on their own. For example, what we call the inner detector is a tracking device. There are magnets in order to bend, charged particles and so forth. Then there are calorimeters, and calorimeters, their job is to just measure energy. They contain everything and they measure energy. The tracking device, they measure momentum and direction. So the whole purpose here is to measure the 4 momentums of all of the particles that are coming out of the collision of, the beams. A beam of proton comes from one direction, another beam comes from the other direction. Here's the tube, which connects to the accelerator that I mentioned before. So a beam will be coming from the left, another beam will be coming from the right. They will collide at the center of the detector. Out of that collision, a bunch of other particles will be born through the Einstein's relation, E equal to mc squared. So energy then gives rise to mass. That means another particle comes out. There will be many of them, and some of them will be charged. As they start moving in the magnetic field by Lorentz force, they will start bending. That's why we have the magnetic fields here. And then the tracking device will start tracking how they are bending so that we can, from the bending curvature, we know their momentum. And then some of them might get into the calorimeter. So the calorimeter here doesn't measure heat, but it measures energy. So the purpose of this calorimeter is to contain the particles that actually get in there, and then will tell you what's the energy. So once you know the momentum, you know the energy, that means you know the form momentum of these particles, and then it becomes a form momentum algebra to figure everything out. Now, so once we have constructed these complicated detectors with 3,000 engineers over 20 years, to complete Atlas and test everything and be ready for the experiment, took over 20 years. When I went to CERN the first time, it was still being discussed. A lot of things were not yet completed. And it took still another 10 to 15 years to finally have the detector ready for data. Now, as soon as everything has been checked out and we are ready to take data, then the first thing we have to do is to make sure that the detector is working very well, is well calibrated, is well aligned. Because like I said before, there are all of these components from the inner detector all the way to the outside where we have the muon spectrometer, we have the calorimeter. You can imagine that if your detector is not well aligned, you're not going to measure the curvature very right. So your momentum measurement is going to be wrong, and your form momentum calculation will not check out. So alignment is huge. It took a long time to align the detector components very well. Calibration means that you have to measure something whose energy and momentum you already know. Yeah, that's how you calibrate your detector. So you need to be sure that it's actually measuring things correctly. So it takes a long time to do all of those things. And then we have to convince ourselves that all the particles that were discovered before, I talk about the cosmic rays coming with a lot of particles, people discover some of those things already. We have to rediscover those things and make sure that we discover them correctly. And this plot here is really, really crucial to everything. It's showing you each of these things are particles that people have discovered before. And what is interesting is that people took many years to discover these particles, a lot of work. Almost all of them led to specific Nobel Prizes. So it wasn't easy for people to actually design experiments to discover each of these separately over 30, 50, or 40, 50 years span. And we turned our detector on within a few months, all of this just started cropping up very, very quickly. And this was in 2010. So that's like within the first year or so of the experiment. And what is interesting in physics is that when you are doing this sort of experiment, not only one thing is to check out, everything has to check out. That means the height of this peak, for example, we know what it is. It's related to the rate, how often that particle is created and decays. So that height has to check out. The width of the peak also has to check out. We know how wide that particle distribution is, and it has an intrinsic width which comes from nature itself. Then the detector resolution adds something. All of those things has to check out. So the height of all of these things have to be correct. And then the position of the peak, the center of the peak is what we call the particle mass itself. It has to be correct because it has been measured before it's already discovered. Yeah. So if your detector is not well aligned, if your detector is not well calibrated, You may see some peak over here, but they will all be smeared at a different position and nothing is working out. Yeah, so this is really a remarkable achievement, that things that were discovered over the span of 50 years and led to different Nobel Prizes because they were each complicated to be discovered. Some were unexpected, they just show up and people discover them, they got Nobel Prize and so forth. We turn our detector on within a few months, everything comes out at the correct position, at the correct height, and with the correct width. The detector is working perfectly. Now we can go ahead and start looking for new particles. Okay, so we started, the one we really want to look for the first is the Higgs boson, the one that gives mass to fundamental particles. A lot of theories, just like Devon, have worked very, very hard to give us simulated information, how this Higgs boson should decay, and how does it get produced, and so forth. These are some of the things that you see over here, many different ways of producing that Higgs boson, and the probability of producing that Higgs boson in different channels. Theories have worked very, very hard, and how, at the time, since we don't know the mass, they have to do this calculation and predictions by varying the mass, because nobody knows where the mass was. And that's why this thing, the x-axis here, is the possible mass of the Higgs boson, and then how it decays. There are many, many different ways that they predicted that it was going to be decaying. When the Higgs boson, it just doesn't sit there for us to actually discover it and manipulate it. It decays very quickly. When it is produced, it also decays very quickly. It is in the decay product that we try to identify it. Okay, so so there are many ways it can decay, and they predicted the rate. So the y-axis here is the rate or the probability of decaying in this various type of channel as a function of the mass. The vertical gray bar here is where we ultimately discover it, what the actual mass of the Higgs boson. But before we discover it, like I said, we didn't know the mass, so we have to do everything by varying what the mass could be. Okay, and then lo and behold, we started seeing signal. So what you see here, the black points are the real data from the Atlas experiment. And this is one of the channel where the Higgs will decay at. I'll go back here. This is the gamma channel. So here, what you can see here, you should appreciate this. So this is the probability of decay. So that means at 125 here, the Higgs will decay more into what we call the top and anti-top quark. Yeah, this will appear more. Yeah, and the two-photon channel is much suppressed, like a factor of 1,000. Yeah, suppressed compared to this one. Yeah, but nevertheless, when we turn on our detector for the first time, the Higgs two-photon channel, which is shown here, is the one that we use for the discovery. But look at the background. Yeah, you see only a tiny bump over here. The red is our modeling. Yeah, the red just gives you a guide. The detector, when we measure the stuff, we only measure the black. Okay, that's it. That's your data. You only have the black. Now we have to do the modeling to understand whether the black contains background or noise plus a signal. Yeah. So the noise is that dashed line at the background here. You see that it goes over there, the dashed line. And then far away from the peak there is just the dash, it's just background. And you see the size here on the y-axis that is mostly background. And what are those background? Like we have a lot of two photons coming from the detector, coming from the interaction of the protons. They are not associated with decays of the Higgs. So you have proton-proton and you create two photons. There are many of them in the detector, but we are not interested in those guys. They may be interesting to calibrate our detectors, but they are not what we want to discover. We want to discover genuine two photons, which we can be sure is coming from the decay of the Higgs, because Right after the interaction, the Higgs is produced, but it has decayed quickly. We cannot catch him. There are only these 2 photons who are there, but there are many other 2 photons who are around. How do we identify the one that are really coming from the Higgs boson? Well, our detector just records all of the 2 photons. It doesn't tell us which one we are looking for. It just records everything. That's why you have the black. Then we now have to do analysis, do modeling, scratch our heads, talk to theories, and do a bunch of stuff and check ourselves. And eventually we come up with the modeling of the background, which is the dash line. And then after you subtract that background, you are left with a signal, which is the bottom one here. And you see that there is a peak there. The peak is telling us that that's a signal. At this point, the background has been completely subtracted. And so that's one channel. The other channel is the Higgs to, the vector boson ZZ to 4 leptons. And here's the peak again over here at the, 125 approximately, 125 approximately. So this will be where the mass is. So I show here, for example, this is a visual. These are 4 tracks in the detectors. And they all seem to originate from the same vertex, one place, which will be a Higgs boson decaying at that point into these 4 particles that form the Higgs to ZZ. So Higgs to ZZ goes to 4 particles. L here is leptons, which means electrons or muons. And all of these are real data points. Okay, this is not some sort of a simulated stuff. This is really something we measure in the detector. And we just trace it like this to show you how the particles was flying through the detector. And when you bring everything back to the interaction point, they all connect together, which means that they are coming from the same vertex, or they're coming from the same particles, which will be the Higgs boson. And then after that, so these 2 channels were the one that we used to announce the discovery of the Higgs boson in 2012. But then, since theories have predicted all of these other ones, we use the gamma gamma and the ZZ somewhere here for the discovery. But there are others predicted by the standard model. Well, so if the standard model, our model is right, the other one should be there. And in particular, this BB. And I told you already that at 125, there should be more BB than even gamma gamma. Why didn't we discover the BB for the first, much faster? Well, it's because things are complicated in life. It's easier for us to detect photons very quickly, but a B is a quark, and isolated quark, we don't see them. They always do some gymnastics, and then they produce a shower of other particles, and they are complicated to discover. That's why we did not discover this one very early. We had to do a lot more work, redesign our detectors and our analysis strategies, and look for things that we call jet and so forth, and try to understand the background. It took many more years. Eventually, here's the signal of the BB. Yeah. And the gray part is the background, and here's the signal, and that signal is significant. So we have discovered this one. So what ultimately we wanted to do is to discover the Higgs boson in each of its decay channel as listed over here, to convince ourselves that we are really discovering the same particle at the same mass. And so once you subtract the gray one and everything, you will see that the peak of this stuff is also just about 125. So we are on the right track. Then, since 2012, we have taken many more data. Then the question was, well, when you accumulated more data, was the signal that you saw in 2012, is it still there, or has it been washed out? If it is washed out, then we didn't really discover anything in 2012 to begin with. So that was a big question. So the latter data still show the peaks in the 2 photon channels here. And in the ZZ to 4 lepton channel, the peak is still there. It's just growing stronger and stronger. So there is really no question that we have discovered something. Here's another channel, the Higgs to WW, that also is, we have the discovery in that channel by itself. And Higgs to tau tau, this is the 2 tau leptons. that also give us the discovery practically at the same position. So now basically all of, there are still some other channels that are too weak for us to see. For example, Higgs to 2 muons, they are just too suppressed. That's why we haven't seen them yet. But practically all the decay channels, they are coming together, and the discovery is significant at the same position. Then we started measuring cross-section. So the cross-section is the probability of the of production. Yeah, and I show an example here. Yeah, this is why the theories predicted that there are these various channels in which the Higgs will be produced, and their rates or their probability of production, they are different. Some have stronger probabilities like this one, some have weaker one like this one. And so we started measuring the rates, how often the Higgs gets produced in different production channels. Yeah. And then we compare that to the prediction that I showed you before, which is coming from what we call the standard model. Now, if you compare it to the standard model and it's exactly at 1, that means it's consistent with the standard model, and that means we are measuring exactly what the standard model predicted. So you can see here that within the error bar, which are the horizontal line here, they all cross 1. But there are errors, yeah, just like in any detector measurements and so forth. We have to account and understand the errors that come from statistics, the errors that come from systematics. So the bars are the errors. So within errors, this could have been a little bit away from 1. We don't know, okay? But we know that it's consistent with the standard model because all of the error bars are crossing 1. And then the other things that we measure was the couplings, because, remember I told you that I give the analogy of somebody on skis, somebody with snowshoes, somebody just walking, all of them are being weighed down by the snow, either strongly or not at all. Yeah, the coupling is exactly what gives us that expression. Some particles are strongly coupled to the Higgs. That means they will be weighed down more, they are much heavier. Some are not at all, and they are lighter. So that coupling is proportional to their mass, what the mass is. When we measure that coupling, and lo and behold, everything is on the line. And this is a beautiful result. It's really amazing. The standard model is that dash blue line, and our measurement are the data point. See how beautiful this thing is, from a very small mass of the muons to a very large mass of the Z boson. This is 3 orders of magnitude change. It's an impressive result that I want you to appreciate. The other thing that we wanted to understand is the spin and charge conjugation and parity of the Higgs, of the particle that we have discovered. We know that from the standard model, it should be 0+. And our data, again, is the black points with the error bars. And then we compare that to different type of model. The 0+ is the blue one there. And then we have other one, yeah, and other model here, which is the red. And you see that the data is consistent everywhere within 1 sigma of the 0+, spin asymmetry. So this also has checked out. Then the other thing is that now we know that the mass, when you look at the peak, is roughly around 125. We want to measure it precisely, and we want to measure it in each channel. So in the earlier run, the first one, we had the Higgs to gamma gamma, although it gave us the discovery, its mass was like 1 GeV away from the center. We could not understand it. We checked our measurement, we checked our calibration, it was not understood. Later on in run 2, when we did some refurbishing of the detector and recalibration and everything, the run 2 one came much closer to 125. So you can see all of them are around 125 here. And we combine all of these things to really, set the measurements of the Higgs mass. And then the other thing is that we want, we want to measure the signal strength. I showed you that the entire cross section is consistent within one within error, but we want to know how far away could it be away from one. So that's what we call the signal strength. If it is exactly one, then it's the standard model production. And so here you do statistical analysis and taking into account all of the error, the systematics, and then you come up with this value. So if mu is exactly one, that's the standard model. So you see that it's consistent with one. This is like statistical error, systematic error, the total error. You take this in quadrature, you will see that within error is consistent with one, but there is a deviation. It could be a little bit away from one. If it is a little bit away from one, then it's not the standard model. In fact, we demonstrated that, the decay of the Higgs boson to particles that are not in the standard model, that decay probability could be as high as 30%, and so it's significant that them, although everything seems to be consistent with one, there may be, small deviation may bring, things like, dark matter, which I'm going to talk to you about. It's been observed that, when you look at, how galaxies and are rotating and so forth, they're not going according to the Newton's law. And people didn't understand, why, that you have to postulate the existence of a much larger amount of matter to explain how the curve, how the data is looking. And the first hypothesis was by this gentleman, Franz Vicky. And then this lady also did other measurement of rotational curve of galaxies and also came up with exactly the same conclusion. And here is the plot here. Here's the data. In principle, Newton's law is going to give you this curve, and this is the data at the points over there. You have to assume that there's a huge dark matter in order to match this observation. So that's where the idea of dark matter comes from. So there is matter. So I told you about ordinary matter. I told you about antimatter. Now I'm telling you about dark matter. Yeah. Dark matter is matter that we don't know the nature of, we don't understand it. We know that it exists because we have to postulate that to explain, a data like this, like how galaxies and these things are rotating, and they are not explained by Newton's law unless we assume that there is much more matter that is around. So the Higgs has been discovered. We confirm it in later measurements. We've measured its properties. I showed you the mass, the spin, and the rate and all of those things. Now the question is, can we search for new physics in the decay of the Higgs or association with it? I showed you that the signal strength is a little bit, not necessarily one is consistent, but it leaves some room. Yeah, I also told you that in the decay channel, up to 35% of the rate could go into 34% can go into these extra particles that we don't see. So that's where I am looking at. I'm doing my searches right now. So with this dark matter idea, what people have done now is to postulate the existence of a dark sector. Yeah, the standard model describes our real sector here that we know of. And then there could be a dark sector around where dark matter particles are there, other dark particles are there, and they call it dark simply because they don't interact too much with us. There are some mediators that are responsible for the interaction, but they don't really interact too much, okay? You can imagine, for example, that, maybe it is, I don't know, alternative universe that is not interacting with us too much, yeah? So that's the dark sector. It can appear, its effects can appear in the visible sector, and that's how I search for it. We search for dark sector state. So somebody like Devin has to write down for me the equations, the Lagrangian. Yeah, the Lagrangian is basically the reformulation of Newton's law to describe the equation of motion. Yeah. So with the existence of new particles who also have the kinetic and potential energy, then I will go to somebody like Devin and say, give me the theory, write down the Lagrangian, and then we will solve for the equation of motion. And here, the Lagrangian, for example, it will start with the standard model Lagrangian that we know with all of the standard model particles. Then we'll say, okay, the dark sector has a bunch of particles, so there will be the dark Lagrangian also. Then there is a mixing between the dark sector and the ordinary sector, and that mixing parameter is the kinetic mixing. As an example, there may be different portal. This is what we call the vector portal, because it's just like the Maxwell's equation. And then there's the Higgs portal. So these are all the window into the dark sector. So you add all of those things to the Lagrangian. I won't do it. I'll go to somebody, a theorist like Devin, to do it. And then I will go and measure it by checking the theory with observation. So in the dark sector, there could be what we call a dark photon. We know photon to be a particle of light. So then somebody is telling you about dark photon. Okay, that just means another photon in the dark sector that is not our standard model photons. And that dark photons, which is A prime here, could decay into standard model particles like the electrons and the positrons. They could decay into particles that are stable, that we don't see in the detector, that carry away energy, and so forth. And people have projected how we can search for those particles. In this plot here, the kinetic mixing parameter, which is the mixing between the vector dark portal and the standard model as a function of the dark photon mass. Yeah, so it's a 2D plot, and these various colors are the different experiments. Some of them have already completed. Some of them have been proposed. Some of them have been analyzed. They are excluding different region of this parameter space. So the white place that you don't see anything in there, that's just the room where this value of the kinetic mixing can still be viable with the corresponding value of the dark photon mass. And this is the projection into the future. Now, this kinetic mixing parameter, it could lead to what we call long-lived particle. I told you that the Higgs decay promptly. It gets produced before even travel. It has already decayed, and it's in a decay product that we search for it. But these dark sector particles, they could be long-lived. They get produced in our detectors. They fly around a little bit before the decay. And that's what we call a displaced vertex, because they are not decaying at the place where they were produced promptly. Yeah. And Atlas and CMS also is in the business of looking for long-lived particles and also prompt particles. And one of the things that I do is to search for the Higgs decays to these dark sector particles in the Higgs portal model, where there could be another Higgs boson in the dark sector. We have discovered the one in the standard model, but the dark sector, if it exists, may have its own Higgs, which dictate the masses of the dark sector particles. So the Higgs in the dark sector and the Higgs in our standard model sector, they could be mixing with each other, and that leads to other phenomenology like this decay. For example, we could have a dark vector boson. So this A prime dark photon or ZD or whatever, they are all the same. In the standard model, the photon is massless, but in the dark sector, that photon may not be massless. That's the only difference here. And we have searched for these things. There could be different type of mixing. This dark vector boson could mix with the standard model Z. So there are other parameters we can search for. And so we've searched for these things. We haven't seen it. So here's the data again. The red, blue, and green are different model of this possible Z dark particle. Keith Baker may have talked to you about this when he was giving his lecture here. We didn't find any excess. So this is just the model, but you see that the data is here and it's consistent with the background. Okay, there's no peak here anywhere that we found. Then we place a limit. If we don't find what we are looking for, we place an upper bound on the parameter. We say that, given the uncertainties in the measurement and the model that we have, we are certain that at 95% confidence level, this kinetic mixing parameter must be less than this. It cannot be higher. Yeah. So that's what we call by upper bound or upper limit. And we search for this other decay as well. And here you can see that there's a hint of an excess. Okay, you see how these two data points are far away from the background here, but they are not significant, statistically significant. We need more of that to define a peak for us, a peak for us. So when we see this thing, we cannot be too excited. Just be fluctuation of the data. Yeah, it needs to be a lot more to be statistically significant, and so far we haven't seen it. The other thing we are looking for is this invisible Higgs. Invisible is what? We have a detector, and now we're talking about something invisible. So a neutrino, for example, is a particle that will be mostly invisible. So it's a particle, we know that it's in the standard model. We have seen it, we have detected it, but normally it's a particle where when it gets into your detector, it hardly interacts with anything. For a particle to be detected, either it's being deflected by a magnetic field or it leaves some energy deposit, either in the calorimeter and so forth. And those are the things that we measure to detect the particle. If that particle gets into your detector and just flies away, then it's called invisible. It means that we have no means of detecting it directly. Yeah. So,
Ketevi?
yes?
Maybe 5 more minutes.
Yeah, that's fine. I think I'm also almost done. So the Higgs could decay into 2 invisible particles, and those invisible particles could be signature of dark matter. So I look for a signature like that. And so how do we measure invisible particles? So what we do is just basic kinematics. We measure all the other particles that are visible, the one that are tracked by magnetic fields or that deposit energy and so forth. We check out all of the form momenta. We know that there are 2 protons that are colliding. Those protons, they also have the form momentum. So you just do a form momentum conservation. And then, the missing amount of momentum and energy that you have to add for the form momentum to conserve is the one that is carried away by the particles that is invisible. So that's quite remarkable and very simple concept. And we did that. We didn't see any excess at all in searching for invisible particles. And then we do an interpretation of dark matter. So we compare with people who are searching directly for dark matter particles. And these are, again, exclusion plot. Here are the Atlas plot, for example. Anything above here is excluded. The dark matter can be a scalar, it could be a vector, and that's why you have these 2 different lines and so forth. Yeah, and this is done as a function of the dark matter mass, because again, here we don't know where the mass is. Until we discover it somewhere, we won't know where the mass is. So I organize a workshop, a biennial workshop every 2 years, because my business right now as a search is in this dark sector state. A lot of people come, 70 people, expert comes every 2 years, and we discuss all of the searches of dark sector states, not just at the LHC, but in many other experiments. We were supposed to have one this year, but it has been canceled because of COVID. And the next one will be in 2022. So that brings me to my conclusion. The standard model of particle physics has been very successful. You've seen everything that I showed you. Dark matter may be one of the particles in the rich dark sector, which we are looking for. They interact weakly with the standard model sector. Now, the discovery of the Higgs may give us a probe to the dark sector, a portal to the dark sector, so we can use the Higgs boson itself to search for dark sector particles. That's where I do my research. So far, we have not seen any signal for dark sector particles. Okay, so I will stop there.
Thank you, Ketevi. I will give the group a hand clap from the community. Any questions from anyone? Please raise your hands and I will recognize you. Maybe I will start first with my question. Can you tell us a little bit more about the African School for, good.
Yes, I also organized the African School of Physics. This happens in different African countries. I unfortunately didn't add any slides here. I was just concentrating here on my physics research. But it also happens every 2 years. There is one that should have happened in Morocco this year, but it has been postponed to next year. If the COVID situation improve, then we will have the school next year in Morocco in August. But it started in 2010, and we get of the order of 65 to 70 students. to the school. We also have a mentorship program where we bring some of the alumni to US university, US institutes. There were 9 that came to BNL last year. So it's the whole program is not just a 3-week school every 2 years, but it's a continuous program where we try to support and assist African students who are studying fundamental physics and applied physics. So it's not really just a particle physics school. We have materials physics as well. We have medical application. We have astrophysics and cosmology. We do get also some international students. There has been 1 or 2 US students who participated in each school. So that's what I do. I do a lot of outreach and education stuff in Africa through this school. So the website is just www.africanschooloffphysics.org, just like that. And then you will see a detail of what we are doing. Right now, I am doing with a number of African students, we are analyzing COVID-19 data of African countries. There are 10 countries that we are looking at. So we are modeling the data and then trying to understand the evolution of the pandemic in Africa and then try to draw some conclusion. For the first 3 months of the pandemic, we released a paper that is under review right now, and the analysis is continuing for a more extended paper that is going to come in a month or 2. And so these are all African students in Africa. Some of them are going to graduate school in Europe, but we meet every week and we discuss the progress in the analysis. So I do that sort of things. It's been very educational because we have to do mathematical modeling and bring in a bunch of stuff. One of the things we are struggling with is that nowadays people are doing a lot of things online, but for somebody who is sitting in Africa where the internet connectivities could be an issue, it's not easy to just go online and connect with Zoom meeting for an hour. Sometimes these students have to buy internet themselves or buy data to be able to connect to a meeting like this on the small cell phone screen and things like that. So we have serious challenges. So, but everybody is motivated and so far is going very well. So by all means, please look it up, www.africanschooloffphysics.org. And like I said, we do accept a few non-African students to the school, and also lecturers come from all over the place. And so I think I have to invite Devon to the school in the future.
Yes, I'm trying to invite myself for some time.
Definitely.
We have a final question.
Okay.
Please, sir. Samid?
Oh, I was muted. I'm sorry. Hi, I am a student from the computer science department, so my questions may not be like very precise or specific, so sorry about that. I really enjoyed this talk. It was very fascinating, so thank you for that. I wanted to ask, if the dark photon is not massless, as you commented, then does it travel slower than a normal photon? And have these been detected? Or can they be detected by a normal photon detector?
Yeah, because it's the dark photon may not be massless, so it's it could be a massive particle. So then it will not go as fast as a photon. So it will, in the relativistic scale, then you will have the gamma factor, which will dictate the limit of the speed. That square root of 1 minus v square over c. So depending on how the mass is, how large the mass is, it certainly will not be, it may not be as fast as a photon, but the electron already has such a small mass that is close to the speed of light, but it still has a limit. And the dark photon also, we don't know where the mass is. A lot of people are searching for it, and it could be detected in the same photon detectors. normally it would decay into a pair of positrons or decay into a pair of muons, and those particles can then be identified in similar detector as you have for photons. For example, when we have our calorimeter, we call it electromagnetic calorimeter, and it detects photons, it detects electrons and positrons. So if the dark photon gets in there and decay into a pair of electrons and positrons, that calorimeter will catch it. Yeah. So people are constructing different type of detection system depending on which mass it may have, just like we didn't know the mass of the Higgs bosons, and we have to design general purpose detectors and so forth. So there are, you know, many different detectors like that, and they are focusing specifically on some ranges of the mass of possible mass of the dark photon and possible ways that dark photon can be produced.
All right, thank you. So thank you again for the wonderful talk. Everyone, we're going to go to our after colloquium Zoom meeting, which is your tea and coffee time. Thank you again, Ketevi, for coming. And if anyone has any more questions, then please there's a time to talk after the colloquium. So let's thank Ketevi again. And I guess